Okay. So, continuing from the yesterday's class, I will use those mode to mode energy transfers to compute useful quantities. One of them will be energy flux, and which is very useful for understanding turbulence. So, that is what is the topic now for this one, energy flux and shell to shell energy transfers. Okay. So, I will focus mostly on energy flux. So, let us just try to motivate how to come to energy flux, and some of it, well, there was a question yesterday, what happens when there are more than one triad? No, in general we will have many triads. If I look at fluid flow, the example is in the atmosphere or in normal systems, we will have many triads, but we can easily extrapolate our result to work with more triads. So, this is what I wrote. No? This is the full energy equation coming into way number k. So, this is modal energy, right. So, the modal energy which is getting contribution from a single triad, well, getting contribution energy going from, in fact we know energy going from P to K with UQ acting as a helper, but there are many P's. Now, look, we derived yesterday energy transfer. So, let us use this K notation. So, if I do this, K equal to P plus Q, not K prime, K P Q. So, K equal to P plus Q, right. So, here in one triad we get energy coming from P and Q. So, this is a formula derived, but I just want to mention this. This was first published in Dar, I am the second one, or okay, Dar, Verma, Ishwaran in 2001, Physica D, this for record PT Physica D, and then some more discussion is on review, physics reports 2004, mode to mode transfer. Okay. So, we did this yesterday. So, energy going from P to K on Q to K or K prime. So, K prime is nothing but minus K. Now, if I have more triad, let us say I have this triad, another triad. So, this let us call it P prime, not P prime, let us call it P2 Q2. So, K equal to P2 plus Q2. Now, from this energy transfer is additive. So, in fact, you can treat this as an example where there are 5 people, you know. So, how many? So, I can make 2 sets of 3 people. In fact, we can make more combinations, but I am one person is common. So, let us say I am common and I interact with 3, and maybe I interact with these 3 as well. So, I just do money transaction. Okay. So, money transaction I will get something from Vinay, and then I will start getting from Shashwat. So, I can just add the transaction, right. So, this energy is additive, you can see that energy is additive. Is that clear? Had it been some other function, then I can't do this operation. Here you simply add the contribution, because this equation tells us that energy is additive, this quantity is additive. So, what will I do? Energy coming into K will be from here I do for one triad and I do it for another triad. So, I derived formula for a single triad was S K P Q. So, P giving to K, then I had S K Q giving to K. I can do the same thing for S P2 giving to K, Q to the helper, then S K Q2 giving to K with P to the helper. I can simply add them, right. More triads, no problem, I can just simply keep adding them. Everybody is convinced with this. So, deriving for single triad was for getting the idea, but once you have done for one, you can do it for any. I mean, you solve one integral of some given sort, then you can do for many, right. So, that is the idea. So, we can do it for many, and we will use it right now after a minute. So, my energy transfer has total energy is this, but it also has few more terms which we need to do today. There were some questions yesterday on what happens when there is a viscosity. So, viscosity will deplete the energy, will take away energy from kinetic to heat, this dissipation basically takes it to heat, and this is external force. External force can feed energy, like for example, we saw how convection can feed energy, temperature through buoyancy feeds energy. So, this Fu is energy coming into kinetic energy from external force. Okay. So, if you recall, this was Fu k dot u k star, a real part of this. Okay. So, now we can basically you can add more terms. So, as I just said, my energy coming into P, energy coming into K, modal energy is gaining something, is just sum of all the transfers with all P's. So, here I had written it, I just erased it, from everywhere, from P to K, Q to K, P2 to K, Q2 to K for this 2 triads. So, you just have to sum over all triads. Okay. So, this is total energy. Now, it is very easy, I just in one line, or in fact one formula, I just say this is the total energy coming via nonlinear term, and I will show you how the Creighton formula is deficient. It cannot capture some quantities because they do not have this nice formula. Okay, we will come to it towards the end. Now, this is coming from force, external force, and this coming from dissipation. Dissipation is du is always positive, so minus du will always be negative, and Fu can come with both the signs, and this quantity can also come in both the signs. So, if it is negative, then that means modal energy is losing. The modal energy K is losing to other modes. If it is positive, this one, then is gaining from other modes, and this is totally nonlinear. Now, there is a notation. This quantity is called also TUK. So, energy transfer via nonlinear term, ET via n ln. Okay. So, these are notation in textbooks, it is called TU. They do not, well, in the textbooks they write this is TU. Okay. Our contribution is that we write this as sum of P. Okay. Now, I will use this relation, and as I said, du is this one which is coming from viscosity, and Fu is Fu. So, this I just wrote some time back. Okay. So, now what I have done here is with many triads with force included as well as viscosity included. Now, so if I just sum this over all wave numbers, now that was for given k, remember the old equation. Now, you do it for all k's. So, this gives you total energy, total energy. So, right hand side there is this, earlier there was sum over P, now I have sum over K. Now, there will be, I do have think, okay, I am turning off right now the viscous term in the external force term. So, what is this quantity? Now, I give the answer, but what is this? Are you convinced it is 0 or not convinced? Because so this is energy exchange among themselves. It's like a party where they are exchanging money among themselves. So, A gets from B and B gets negative of that from A. So, overall K to P, and if I just sum over P, when the sum for P comes is negative, it is just quite trivial. You do not need to go, basically in any room, if there is any transaction, overall there is no gain for the whole room, right, when it just exchanged. So, A loses to B, so A will be positive, but when you sum over B, how much B has gained is negative. So, it just totally is 0. Okay. So, this comes quite often. If you do double sum, if A to B equal to B well minus of B to A, then it is 0. So, this 0 is coming basically because of one property which we did in the last class, S k p q plus S p k q is equal to 0, because k giving to p is equal and opposite to p giving to k is equal and opposite to k giving to p. Okay, so you will get this sum. When I do the double sum, this will come always in pairs and they give you 0. So, this is reinforcing our earlier statement that nonlinear term conserves total energy in Navier-Stokes equation, right. We did this for when we solved for in real space, we also solved in Fourier space. I could show that it is 0. Real space I did so for periodic boundary condition or vanishing boundary condition, this is true. Now, I am doing Fourier, that means I am in periodic boundary condition in general. Okay. Now, we can modify our vanishing boundary condition also to Fourier. So, let me make this statement because I will come back to it maybe later, that if this vanishing boundary condition, then I can use sine function. The sine vanishes at the both the points. So, a sum is not exponential e to I k x, which involves both sine and cosine, but I am taking some terms of that. Okay. So, it is possible, but we are assuming right now this is periodic, just assume periodic boundary condition. Okay. So, this is same result as before, that for periodic boundary condition my total energy is conserved for Navier-Stokes equation via nonlinear term. Okay. So, this is same statement. So, we should be able to see that result even with this new formalism. So, this conservation of total energy but okay. So, this is true, but now with mode to mode we can discover some more finer results. What is the final result? I can do this for any region of Fourier space. So, region of Fourier space has some wave numbers. So, it is also true, as I said, there may be money transaction between among all of us, or we can have sub transaction between some set of 3 or 4 people and cut off the other transactions, okay, or you do not count the other transactions. So, I do not mean to say cut off means is like non interacting. We want the interaction to be there, but we only count the ones which is among some set of people. Do not count, like I may be getting money from other people, but I do not count that money. I count only among whoever I am interacting with. Is that clear? So, we call this region A. So, the set is A, set of modes is A, and if I sum over k prime and p, again there will be pairs, and that pair when you sum it up will get 0. So, this is true even for a set of modes if you keep only subspace of those modes. Okay, this is useful quantity for this thing. By the way, please keep in mind this is only for hydrodynamics. If I include magnetic field, that may not work. This is a proof. Is that clear? And this will follow from this relation. A to B is same as B to A with a negative sign. Okay, now I define spectral flux. So, I want to say that in energy flux in usual physics is what is energy crossing a unit area per unit time. That is what you say, no? I mean, the particles hitting an area, then you say some energy is crossing this area. So, any quantity in fact is defined. What is flux in usual physics is that quantity crossing, the flux of that quantity crossing per unit time per unit area. But here, and that is normally, well, depends, it could be so that is a definition for particle flux, energy flux and so on. But this flux is very different. This flux is energy going from one scale to other scale. So, let us draw this. This is in Fourier space. Okay, one thing, this is not in real space, and is defined as energy crossing this wave number sphere, energy coming out of the wave number sphere via nonlinear interaction. So, the modes here inside this in this yellow sphere will interact with modes outside, right, nonlinearly. So, there will be some energy going out. You sum up all the energy going out of the by this nonlinear interaction, sum all scalar quantity, it is not a vector quantity, okay, it is because it is summing up the energy. So, it is sum of all the energy going from the modes inside the sphere to outside the sphere. Okay, so, let me write this. So, total energy transfer from the modes inside the sphere, all the modes, okay, to the modes outside the sphere. Is that okay? For consistency in our numerical simulation, we also keep inside means including the surface modes. So, inside I include the modes on the surfaces, because surface guys say, well, count me in, so either you have to count for outside or count for inside, we count from inside. There will be problem with energy balance, I mean there will be some missing out if you do not count them. Okay. So, how will I write the expression now? So, this was in fact is quantity postulated, well, Kolmogorov did not really postulate this, but this is understanding that this is large scale, no, inside is like wave number is inversely proportional to length. So, this means larger scale and outside will be smaller scale compared to the ones inside the box, inside the sphere. So, the energy going from large scale to smaller scales is like many cascade, I said, from let us say from one bigger companies to smaller companies. So, this is what is this flux means. Now, it was computed by Kreknen, in fact he gave a formula, Kreknen, using combined energy transfer, and the formula is quite complicated. Well, it involves quite a lot of derivation, but with mode to mode is straightforward. So, how will I write this formula with mode to mode? I have the SKPQ, right. So, the giver should be where? Inside the sphere, and receiver should be outside the sphere. So, that is it. So, we write this flux. So, this radius of the sphere is k naught. So, we have this stuff. So, P is a giver, must be within the sphere including the surface, and the receiver is outside the sphere, k greater than k naught. Carrier can be anywhere. Actually, it is not anywhere, it comes from the constraint q is equal to k minus p. But carrier could be inside the sphere or outside the sphere, that is immaterial. And that is where Kreknen had a problem, because in combined energy transfer it is S, K, P comma Q. So, both P and Q give. So, if Q is anywhere, then this guy does not know how to count them, whether it is in the giver zone or in the receiver zone, and that is precise the difficulty. So, Q is indeterminate, and that is where we have to account, I mean he had to account properly, and that is why the derivation is long. Okay. The formula is, which I will show in the later part of this, well, I will not prove it, I will just state the result. Okay. Its proof is quite easy with a modern perspective, but it is quite long with in the Kreknen's paper. Okay, is that clear? So, this is how we compute flux. Now, we also can get this flux from some other formulas. In fact, we need some more, well, this is a formula for flux which we use it for computing in computer simulations and various calculations, but let us see it from some other perspective. So, this is a formula, well, I wrote a formula without the sum, this sum was not there, no. So, remember d by dt of modal energy is T u k f u k, and this. Now, I am just introducing the sum for modes outside the sphere. So, what does it mean? This corresponds to sum of the energy of the modes outside the sphere. Are you happy with this? So, this d by dt of the energy in the Fourier space outside the sphere, outside sphere of radius k naught. Okay. So, I had this box which includes all the modes, but you exclude the modes inside. Okay. Now, this will be nonlinear term. So, this is sum, this is also a sum over force contribution and this dissipation space. Now, let us look at this term, sum of T uk. Now, I will show you that that is equal to flux. In fact, this is also equal to pi k naught. Okay, how will I prove it? Now, let us use our idea of mode to mode. So, pi k naught, this is my question mark, is it true or not? So, I have one definition already I gave you, P within the sphere and K outside the sphere. Now, we will see whether that formula matches with this one. So, I wrote what is T, T uk. T uk is this. Okay, this was done 2 slides back. Now, this sum is coming here. Well, I put now the k prime is same as minus k. Okay. For energy, you can interchangeably change it. So, k prime or k. Now, this can now P. So, k prime is greater than k naught, but P can be anywhere. Okay, and Q will come from k minus P. So, I write this sum, 2 sums, P less than k naught and P greater than k naught. Because when I summed it, this one is k is getting, but k is getting from all P's. So, are you happy with this? This I go from step 2 to step 3. Now, what is there are 2 terms in the step 3. So, this the second term is 0, because k prime is greater than k naught, P is greater than k naught. So, I said no, this is true also for any specific region. So, this is that quantity for all the sphere, all the modes outside the sphere. If the giver and receivers are the same region, you sum it up, you will get 0. So, this is 0. So, the left hand side is this is. Now, isn't it exactly the same formula which I wrote in the last slide? So, P is a giver which is inside the sphere and k prime is the receiver which is outside the sphere. Okay. So, this indeed is our flux. In fact, this is one of the steps of Krecknan's derivation, but of course, he does not go through this derivation, but he argues in different ways. Okay. Now, if a sum over T uk over all k, then what will I get? 0, no, this we showed, this is 0. That means, so from here I do this is T uk k greater than k naught plus k less than equal to k naught, T uk is 0. This is pi uk naught. So, this must be equal to what? Minus pi uk naught. So, this is by the way, subscript means kinetic, okay, because we will also work with other fields. So, we have notation, the subscript is u means is kinetic. So, this is what I write in the next line. We can also write pi uk as minus of T uk sum over k less than equal to k naught. Okay. So, we can use both. So, this is very useful formula for my next derivation. Okay. Now, this is straightforward, no, this straight away comes from energy equations. Now, we define something called variable energy flux. Now, this concept just wait, I mean forget about variable right now, we are going to derive how the flux varies it from one wave number to other wave number. The flux is function of k, so it is not necessary that it is same everywhere, no. So, let us see how it varies with wave numbers. So, okay. Now, so let us define it. 1D shell spectrum, did it define 1D shell spectrum? Okay. So, let us go back in the earlier slide. Okay, I am going to define 1D cell spectrum. Okay. Okay, anyway, let us, even if I define, I will do it again. So, we have something called modal energy. What is modal energy? Is energy of a mode. So, EUK, which is mod UK square half, is a vector. Okay, well, mod of UK square. So, the energy of a given wave number k. If the system is okay, so if I make a wave number sphere, or let us make a wave number shell. This is a wave number shell. You saw the shell. Now, this is k and this is k plus dk. So, my shell is this. Is it clear to everyone? So, there are modes within the shell. The shell thickness is dk. Now, we define, so if system is isotropic, then modal energy at any mode inside the shell must be equal, right. If I take a mode here on the average, okay, and mode here, since it is isotropic, we expect that energy to be equal. So, it is a good number. Well, we have too many modes. So, well, let us sum them up and get a number for a k, wave number for a shell k, shell of radius k with thickness dk, we can get energy content. So, it is defined like this. So, E of k times dk, okay, is the sum of E k prime over k prime lying between k to k plus dk. Okay, this is the definition. So, if I divide, well, if I make dq go to 0, this quantity, the sum will also be very small number. So, I can divide this by dk, I can get ek. Okay. So, this is called 1D spectrum, 1D shell spectrum. In computer simulation, we make dk as 1. So, shell thickness is 1 in computer simulation, but we keep it arbitrary right now. Okay. Now, that is what I have done. So, instead of summing from 0 to k, 0 to k naught or k naught to infinity, we will now do the sum of E k prime. Now, this is 1D spectrum. So, there is no, this is not a vector anymore, this is a scalar, it is a magnitude of k. So, k prime goes from k to k plus dk. So, right now I am including the, well, this equal is here, equal is here. Now, so I am just doing the energy equation. No, so I made a mistake. This should be k prime and k prime, no more vector. So, I am summing over shells. So, shell has a number. Okay, fine. Now, this TUK, so let us look at the next step now. TUK is connected to flux. Okay. Now, this is for the two spheres, sphere of radius k plus dk, sphere of k is the, this quantity is the difference between the two spheres. I can sum over TUK over the bigger sphere and subtract out from the smaller sphere, I get that quantity in the box. So, so the first quantity is, well, now take the dk going to 0 limit. So, what, well, let us write this one. What is this quantity? So, there is a negative sign, no, minus pi k plus dk, minus becomes plus, is pi of k. Everybody is with me on this? The minus sign because of I am summing from 0 to k plus dk. This one is TUK sum k prime less than equal to k plus dk minus TUK sum k prime k prime less than k. We can make also, now this is, I really should make a k prime for a shell. Okay, is that clear? In difference between the two spheres, and the first sphere is minus pi k, first number is minus pi k plus dk, second is minus of minus pi uk, there is a minus sign here. So this is that. Now if dk goes to 0, then what is this quantity? This d pi by dk, a partial, because it can also depend on time, into dk. Yes. What about this quantity? We can write this as partial d by dt of uk times dk, this one. Dk goes to 0, then I can, any quantity is fx dx. Similarly, this quantity is fuk times dk, this is duk times dk. So dk gets cancelled, but dk is removed, dk going to 0 limit, it cancels. So I get this equation. So my flux is changing with k, also with time, and energy is also changing with time and space. Sorry, time and Fourier k. So this is equation. Everybody is with me?
Which one will be the first cell, the inside or the k plus dk?
This one, this equal to, so this equal to will be here, because equal to is here. The next one is not equal to, excluding that. This is just this sum I am writing it here. Okay. No, actually you are right. So this should be also equal. This should be equal. This both should be equal. So that, yeah, both should be equal, and that's how it is pi uk. Okay.
How you convert the capital N total derivative to partial and energy?
Okay. So what is this quantity? This sum is uk times dk. No. Now, so let's write it here. So the first term above, I have space here, d by dt is uk times dk. Fine. I should put a time here, t, uk comma t times dk. What about the second term here, that coming from t? There is a minus, there is a minus d pi by dk partial dk. What about the third term, or second in the right? Any quantity summing over this is fuk, this is math cal, is called math cal. No? So this is not same as force, times dk. Last term is duk times dk. Now I just cancel dk. No, dk is a finite. Well, dk is a small but finite. So this cancel dk, and we get this equation. Fine. Oh, okay, okay. Oh yeah. So this should be, well, it's okay. It's important. This is okay. Actually, no, I don't want to write. Well, if you want, you can write this is a total in a volume. Now this is function of, okay, we can write this as partial if you like. This is partial. Well, now that will be changing the, so this quantity, this sum is function of k as well as time. So ideally it should be partial. Is I'm fixing k and doing in time. So you can make it partial. Yeah. Okay. Now, so these are the, well, I mean, this I am repeating again. This, the dissipation rate is this. Now let's work on under steady state. So I am going to make the assumption of steady state. So how can fluid turbulence become steady? If I supply energy and wait for some time, then there is a flow of energy to a small scale. So, energy supply matches the dissipation, then I get a steady state. Okay. Like my income and my spending are roughly equal, then I have steady life, my bank balance does not change very much then. It is not a saturation, it's like system is still fluctuating, but it has a, on the statistical average for energy, it's not a saturation, it's evolving, but it does not change on the whole. So, energy of a given sphere or a given shell will not change, it will be average quantity, it will fluctuate around a mean, but the mean will not change, local mean will not change at k. So, steady state is when my force and dissipation are balancing each other, then my energy of a given wave number will not change in time. So, I said, so steady state normally people say that steady state when dy dt should go to 0, things should depend only on k, not on t, but in turbulence of course things change in time, but we are talking about average. So, I sum over a time unit, then is one time unit, then another time unit of same length, I should get the same number. Okay. So, this is statistical steady state, in fact that is the word which is used, statistical steady state. Okay. So, let us look at what happens in statistical steady state. So, my dy dt is gone. So, let us go back to this equation once more. So, dy dt is gone. So, I can take this to the left hand side. So, d pi by dk is fu minus dk for any k, this for any k. Okay. So, for any k d pi by dk, now I dropped, now this is not a partial anymore, this is total because there is no time. So, this partial and total I keep change it according to my situation. So, fuk and minus dk. So, this is local quantity, please remember it is not the total. So, for any k this will work under steady state. So, this is a sphere, our pink sphere, which is radius dk, starts from radius k to k plus dk. Now, we are supplying energy fuk, it dissipates duk, and then need not be equal, fuk and duk need not be equal. So, this pi uk here and here they can be different, but they will not change in time. This quantity is independent of time, this quantity is independent of time. Okay. So, but I know for sure that the difference between these two divided by dk must be equal to fu minus du. So, this is the income and this is the dissipation for this shell. So, if fu is bigger, then what will happen? Which will bigger than duk, then which should be bigger? If fuk is bigger than duk, let us say this, then which one will be bigger, this one or that one? K plus dk should be bigger, no? And if fuk is smaller than duk, then other way around. Okay. In fact, this is very useful conclusion. This is very simple idea, but it is very useful, and this we call variable energy flux. So, our energy flux is changing with k. Yes.
But
no. So, you should treat it as following: fu and du are cause, they are causing things, and pi is a effect. Pi is coming from nonlinear things. So, cause and effect. The right hand side is the source, left hand side is like my variable. So, given the source, so somebody will compute fuk and duk, and with that itself I can compute what is flux at as function of k. In fact, you can solve this differential equation. If I have some single differential equation, if I can write this as function of E, this function of E, this function of E, in principle I should be able to solve it. Okay, that we will do later. Okay, maybe well after the midterm exam. Yes. Well, now the last statement is not correct. Let us wait for a while. Let us wait for this stuff. Okay. So So, I am coming to that. So, I will show you a situation. So, your statement until thing was correct, but after last statement is not correct. So, we will discuss that. So, this is a statement of variable energy flux. My energy flux is changing, and this can change because of external forcing and dissipation, imbalance of the two. Okay, now let us focus on inertial range. So, I am also now going down further and further, narrowing myself. So, inertial range is, what is inertial range? So, so we divide in our wave number space in 3 regions. This is typically done in hydrodynamic turbulence, but that is the follow up I will do. So, there is one region where there is some external forcing. Well, of course I have a forcing sitting here, but let us imagine, well, there is some large scale, do not call it external forcing, there is large scale where the box effect will come into play, the walls and so on. There is a region where dissipation is strong, dissipation strong. In between is the inertial range, where dissipation is ignorable and the wall effect is also ignorable. So, no wall effect, no dissipation, and this is called inertial range. So, inertia means, well, this is a slightly technical, I mean, in the sense, actually I will not say technical, it is community notation. The fluid dynamics notation is u dot grad u is the inertia term, acceleration term, u dot grad u. So, if the region where inertia is important, so u dot grad u is like, it is not viscous term, viscous term is nu grad square u. So, here nu grad square u is important, here some wall effect is important in left side wall, in between is where only the nonlinear term is playing a big role, nonlinear and pressure, okay, both I would say, fine. So, anyway, this is a notation. So, we are focusing on the middle region, and in the middle region I will get this because dissipation is weak. So, I drop the du term and instead of Fu I write F in. So, there could be some force here in large scale, okay. So, I will call inertial In for inertia. So, force in the inertial range. In fact, it is just that I just drop the du term and I look at the local force, okay. So, this is our important equation to look at the property of flux in the inertial range, okay. Now, my next slide is slightly dense slide. So, there are 4 cases. Now, I will go one by one, in fact that will answer your question. So, let us consider a case where my inertial range force is 0. So, if inertial range force is 0, then d pi by dk is 0. So, flux will be constant. Now, flux being constant has 2 scenarios, flux is 0 or flux is a constant value, it can also be negative, but in 3D energy flows from large scale to small scale, so it is positive, okay, in 3D. In 2D it can be negative, but we will do it later. Let us assume we are working with 3D and it is positive. So, the 2 scenarios, 0 and positive. Now, when do you get 0? Can you think of situation where we get 0 flux? No, dU is 0, F is 0, okay. Now, this is a scenario when there are many modes at different scales, but A giving to B is same as any region, and there is equilibrium, okay, this is called equilibrium, but things are existing at all levels. So, there are companies, big companies, small companies, rich people, well there is no small, but this is not possible, no. Equilibrium means somebody has to give, non-equilibrium is Well, rich will always spend more. No, I mean this analogy I like to make. So, there will be more this money flowing from rich to poorer. Okay. So, this is non-equilibrium, that means one is giving more than other. So, what is equilibrium? Is any transaction must be equal, A to B should be same as B to A, not equal and opposite. A gives 5 rupees to B, B gives 5 rupees to A. Okay. So, it is not that B receives. So, by the way, SKPQ, A gives to B was receiving, A gives to B. So, B was receiving, but A is getting negative contribution from B. I wasn't giving it back. So, equilibrium means there is no net coming to anybody. If there is no net energy coming to anyone, then what happens to the flux? Will there be any transfer from any level to any level? No, right. So, this flux was transfer from one scale to other scale, in fact large scale to small scale from the sphere. If there is no this balance of transfer from any to any, then there will be zero flux. So, if I draw the sphere, if A to B and B to A are equal, then what happens? So, it is zero flux, right. So, there are modes outside, that is fine, there are modes inside, but they do not exchange on the average. So, that is like thermodynamics, thermodynamics they are supposed to be equilibrium. So, equilibrium means there is no net transfer. By the equilibrium, well, thermodynamics normally assumes single scale. The molecules in this room are not of different sizes or not having different energies. They are roughly, so this is richer, this scenario is a different scenario where there are different scales, and some bigger molecules, small molecules, smaller molecules, size is different, no, K. So, it is not exact analogy with thermodynamics, it is different, but there are situations where it is claimed to have happened, like Euler equation. When there is no viscosity, then Euler equation has something similar physics as this, where each mode is not, any mode is not giving any energy to other mode. Okay. But we will do this bit later. So, I will not worry about Euler, but this is equilibrium scenario. Second scenario, when there is a net flux. So, there is energy going out of the sphere. So, energy goes from large scale to small scale, okay, in 3D. So, that is a constant flux. In fact, I do some stirring at large scale, I shake up this fluid and that finally goes into heat. So, this is our scenario of hydrodynamic turbulence. And this will lead to Kolmogorov picture, which we will do it after in the next class. Kolmogorov theory says energy flux is constant. By the way, I derived it from energy equation, I did not assume it. There is no net force in between in Kolmogorov theory. Kolmogorov assumes that we supply energy only at large scale. So, there is external force, but that is not in the inertia range. In this inertia range, okay, this between Kf to K di means dissipation. So, these are wave numbers. In this region, there is no force. Is that okay? So, I derived it from energy. I really did not assume anything. Energy equation, put force to 0, flux must be constant. Whether this is independent derivation, so this Kolmogorov derivation is different, which we will do it later in the course. So, this is coming straight from energetics in Fourier space. Fine. So, force being 0 gives you two scenarios. The third is FUK, this one is negative. So, then flux according to this definition, our formula, it should decrease. So, d pi by dk must be negative. So, flux will decrease and I can see that FUK is decreasing with k. So, it is negative, you see FUK is negative. So, my flux will decrease, and this does happen in nature. Now, one scenario is which will I do hope to find time to discuss this, called stably stratified flows. Like Earth's atmosphere, this is stable stratification, high density below and low density above, and I can stir this. In fact, in Earth's atmosphere there is some turbulence, but it is a stable system. So, whatever energy you try to feed in, there is the gravity will, in fact it turns out, which I do show it in those research papers, that because of stability of the system, the external force, which is buoyancy, will take the energy out. So, we can show that this is negative, okay, for stably stratified system. Now, this proof is not so straightforward, but we will do it hopefully later, but we can show for this system F inertial is less than 0. Actually, so this is, since it is stable. Now, let us look at the other scenario when my force is positive. So, this green arrow going into the sphere shell means it is feeding energy. So, my force is positive, force feed, energy feed by external force is positive. So, what will happen to the flux? Flux should increase, which is what your scenario. Now, can it happen, or where does it happen? In inertial range only, but physical system. In real life, we have to find a scenario when this happens. This happens in thermal convection. In thermal convection, we know that buoyancy. So, if the fluid is at rest, so what is kinetic energy flux? If it is at rest, 0, no, velocity is 0. So, UP, UK, everything is 0. If I turn on the heater and so start convection, so what happens? Every sphere has got, every shell has got energy. So, I fed the energy through buoyancy. So, buoyancy is always, this is positive. So buoyancy, well, in fact we know that hot fluid rises, right. I mean, this is, so UZ and times temperature. So, this is energy feed, no. So, buoyancy is proportional to temperature and multiplied by velocity. So, F times U is, in fact, is proportional to this, force is proportional to temperature and I multiply by U, so which is UZ. So, this is positive. Hot, if T is greater than 0, greater than the mean, then UZ is positive. So, energy feed by buoyancy is positive. In fact, this is straightforward proof, and the cold plumes come down. So, T is less than mean and UZ is negative. So, they are come in the same sign. So, here my flux should increase with K. That means lower wave number modes higher wave number modes, small scale fluctuation should become more violent, and okay, this is what we try to do this simulations and analysis. We find that it for relevant convection does not really increase, it is flat, okay, for reasons which are more complex, which I can't discuss right now, but in thermal convection it is possible that the flux can increase, okay. So, this is an example, and the other things like bubbly turbulence when you put in bubble or unstable systems. All unstable systems come in this category. That is my statement. There may be some exceptions, but that is my stable systems come under this category if there is a force at all scales. Unstable systems come under this category. So, variable energy flux can help us formulate or understand the energy flux via this formalism. Okay, so it is very useful, though it is like based on energy and it straight away comes from energetics arguments. You can understand flux, and once I understand flux, I can also say something about energy in a sphere. We call 1D energy spectrum. Okay, so let us go further. So, is that clear to everyone? I mean, this is important, we can discuss some more. So, let me just summarize. So, d pi by dk is F inertial k. Now, if F inertial is 0, then I have two scenarios, my flux is 0, which is equilibrium. Flux is constant, it is non-equilibrium. I also would like to say that this is non-equilibrium. So, thermodynamics ideas do not work here. There is a net transfer of energy from one scale to other scale. So, there is not equilibrium means A to B is same as B to A. There will not be change in energy, or there will not be any transfer, net transfer in equilibrium, but here there is a net transfer, though energy does not change, mind you. So, whatever I get, so this big is supposed to be whatever I get, I must pass on at a smaller scale. But the question is, why does energy is more for a given scale than other? Here you will find typically the energy is larger at K1 compared to energy at K2, when K2 is larger. Why it is so? Because there are more modes here. So, it's in fact this analogy is reasonably accurate, that there are poorer people, more people with less money receive from fewer people with more money. Looks like there is some kind of inequality is built in this non-equilibrium. This is unequal, no, when there is few poor rich people. So, energy is more here because there are less rich people. The number of modes in a wave number K1 is 4 pi k squared. So, lower k, less number of modes, and so we will discuss some of it later when we do turbulence, but this net transfer, and when when Fu is negative, and then my flux should decrease, if U is positive, flux should increase. Okay. Now, let us go further. So, other flux is Krecknen formula. So, Krecknen wrote this. Okay. So, this is Tc minus Td and Tc. So, this is Krecknen formula, no, combined energy transfer. It turns out we can write this as pi by 2, and this is minus pi by 2. So, this is there in the notes, you will find this, and if you I can prove it quite easily. In fact, the proof which I gave you some time back, just use that. This is factor half, no, this half is here. So, this is basically flux and this is negative flux. I did show that, I mean this is what. So, with mode to mode it is easy to show that Krecknen formula is correct or consistent, let us say this way, and this by Frisch. So, here this is a receiver mode, no, u dot grad u dot u, well actually no, this is a receiver and this is a giver, and he has put a. So, I would like this to be less and this to be greater, no, but it turns out it gives the same answer. The receiver is outside the sphere. The less means in terms of size. So, anyway, this is the formula in his book, but it turns out it is consistent, and this is a mediator. Mediator is anywhere, it does not have less or greater sign. Okay. So, this is about flux, but we can get more detailed picture by something called shell to shell energy transfer. So, the related quantity is shell to shell energy transfer, which gives you more information. So, flux was energy going out from inside sphere to outside sphere. Now, we can get more detailed picture by this energy going from shell M, this shell M. Okay, there are two shells I am drawing here. This is again Fourier space. In yellow shell is shell N, M and shell N. Okay, so we just label them. So, these are supposed to be lot of modes in that, shell M and shell N. Thickness, do not worry about it right now. I am not telling you that they are same thickness, but they are shells. So, we can think of energy going from shell M to shell N, right, or shell N to shell M. They are two different regions. If it is equilibrium, of course, then it will be 0, but non-equilibrium there will be transfer. So, how do I compute energy going from shell M to shell N? So, here the notation is this shell to shell transfer T, the giver is above. So, M is the giver and N is the receiver, and the first symbol is field, Right now I am thinking only about velocity field, but when you do MHD then we have magnetic field. No? So, that is the notation we keep U is a so this is a field. So, right now is U to U, but we want to keep the same consistent notation, that is why we write that here. So, how do we compute this? By shell to shell transfer, by mode to mode transfer? Straightforward, no? The giver is pink shell, modes in the pink shell, receiver is modes in the yellow shell. So, P lying in, P is part of shell M, belongs to, and receiver belongs to shell N, and just sum it up, right. So, this is one line. So, this is how we compute. Now, if you use Craiglang formula, then there is a problem. Can you see the problem in Craiglang formula? Craiglang is K receiving from P and Q. Now, it is a triad only, no? So, we need all three. So, it is possible the PQ lies in pink shell, or P lies in pink shell and Q lies anywhere, Q could also be in yellow. So, Q does not lie in the pink shell, okay. So, that is ambiguity, that is so in Craiglang formula it is not possible to compute shell to shell. So, I will give you some examples which people did try to compute with the Craiglang formula. So, these are names Waleff, Zoe, Domorodski, and they give a formula of this sort. So, half SU K P comma Q, PQ lying in M, both of them lying in M, and K lies in N. Now, will it give you the correct answer? So, what will it give you? So, this is a picture here, you can see the picture, smaller picture, PQ lying within M, and P is lying here and Q lying there. So, it is only the triads of type A. So, I can write this combined energy transfer as two terms, right, this one, this is by definition combined transfer. Now, this is a definition, no. So, this half is basically I am doing the sum twice. So, this is shell the modes triads of type A. Triads of type B is not included at all in this. So, triads of type A, type B is not included. So, this is not correct. So, this is where the mode to mode formula wins. It can compute the shell to shell transfer exactly, and this is a problem with quite a few papers. Okay. And there is a variation which I discuss in the book, but I will not discuss that. So, triad B is missing in this. Okay, we can also talk about energy transfer from any region to any region. So, region A to region B. So, for anisotropic turbulence we define rings, so not shells, we can go further down. So, like in a earth we can think that dynamics near the pole region is different than near the equator, right, because it is anisotropic, there is more heating at the equator than at the poles. So, we can define this that P belongs to A, giver, and receiver belongs to B. So, this will be region A to region B, it should be ring or it should be any region you like, and this can give you energy transfer from one region to other region. So, this is a very useful formalism to compute various types of energy transfers. So, there are three types: flux, shell to shell, and in fact generalized any to any. So, one example I am giving is ring. So, ring is, so shell was this, no, one shell to other shell, but you can have a ring like this and a ring here. Well, I am sorry, I should join. So, the ring here, equatorial ring and polar ring. Anyway, we will do that later. So, ring to ring I did not really draw a picture, but it is general. Okay. So, stop here. Thank you.